Next up is cyclooctave. This is very similar to cyclobutadiene. It's anti-aromatic, has 8 electrons, but you add 2 electrons to it, make the diane ion. Now you're at 10 electrons. That's aromatic according to Huckel's rule, right? 4n plus 2, where n equals 2, gives you 10 aromatic species. So this is a pretty large ligand, so you can have a lot of different binding modes. You need those 2 electrons, extra electrons, to make it aromatic. But then, not necessarily all of those electrons are going to be involved in bonding. So you can have like an 8-4 complex, 8-2 in 2 different spots, or 8-6. You don't have 8-8 with D metals. There's just too much steric hindrance there for such a high coordination number. You can have stable complexes. So here's a 8-2 with iron. That's a stable complex. 8-8 you can have with the 5F metals. So these are the actinides, right? So uranosine is an example of this. Let's go on to benzene. Benzene's an aromatic, so it's a little bit different, but there's nothing you really have to do to this. It's neutral. It can be a ligand. Bis 8-6 benzene chromium is by far the most common complex. This is very stable and can be used as a ligand. This material actually you can sublime and purify it just like ferrocene. The alkyl ligand can have 2 different binding modes. Alkyl, remember, is a double bond. In organic chemistry, is a double bond with a single bond, and so you can have an 8-1 type interaction that we talked about earlier. In the electron counting convention that we've been using the neutral or the covalent model of electron counting. We would call this a 1 electron donor. If you're using the ionic model, you'd call this a 2 electron donor, but your book talks about both. We went over in the previous lecture videos in chapter, I'm not sure what chapter it was, but when we went over the 18 electron rule, we went over the neutral model. So we said that HX, if HX is a stable complex, then that got one, we call that a 1 electron donor because HX is neutral. And so yeah, HX with this, if you add an H to here to this alkyl, and all you're doing is binding through this spot, that's a 1 electron donor. Now, alkyl can also, and more commonly, is a 3 electron donor like this. Okay, now there's 2 different resonance structures. So that's a 3 electron donor in our way of electron counting. Why is that? Because you get 1 electron from the charge, and then you get 2 electrons from the double bond. So you can draw 2 different resonance structures like this, or just draw it like this. This would be an 8-3 case. Here's a palladium complex, mu chloride palladium complex that's well known. That's 2 alkyl ligands binding in an 8-3 fashion. Cyclopentadiene, very common organometallic ligand. This one comes from cyclopentadiene. That's not aromatic. It's not even conjugated because it has a space here. But if you deprotonate this and make this C5 H5 minus, now you have a conjugated system. Okay, so you have 6 electrons, and just like benzene has 6 electrons, it's aromatic. And this, by our nomenclature, if we would call this actually a 5 electron donor. It depends again what model you're using for this, but we would call it a 5 electron donor. And why is that? Because HX is stable, right? So this is, you get 1 electron from there, and you get 2 electrons from this double bond and 2 electrons from this double bond. If you're using the ionic model, though, this would be 6 electrons because you count this for 2. You can see your textbook about that. You just have to choose one way of doing it, and then you'll get an answer that's fine. Ferrocene is very stable. It also sublimes. You can purify it, get these nice orange crystals. You can, there's all sorts of different transition metal ferrocenes transition metal metallocenes that have been explored with cyclopentadiene ligands. You can also substitute the ferrocenes. So you can have like decamethylferrocene. That would be a lot more electron donating. So people are interested in electrochemistry, for example, like this, because this will change the redox potential of iron. Or you can add fluorine atoms on there and change the redox to something very electron withdrawing. So there's all sorts of games you can play. And the last ligand we're going to go over is cyclohexatriene, very similar to cyclopentadiene, not as common, but same idea. But now you're going to make a cation instead of an anion. So you're going C7H7. So you're still deprotonating it, but now you're putting that electron density, right? Because you had two H's here, and so now you're just, you're going to pluck off one of these hydrogens, and this is going to be aromatic because it has six valence electrons as well. And you can now move the positive charge, around the ring, and so it is conjugated. This right here, it's not aromatic because it's not, there's a gap here, okay? And so, yeah, you can have complexes, 8 to 6 complexes of cyclohexatriene that behave very similarly in a lot of ways to cyclopentadiene. So, all right, so that's sort of our just short overview of organometallic chemistry. You could teach a whole course, and people do. There's a graduate level course taught that's very good that we teach occasionally in the chemistry department on just organometallic chemistry. But hopefully this gives you a flavor of really the vast chemical diversity that can exist in the structure and reactivity of organometallic complexes that largely comes due to the diversity in the different hydrocarbon ligands as well as the phosphines. That's really where you get a lot of the diversity, a lot of the different electronic and steric effects that you can play with these different substituents. All right, guys, so very good, and I'll see you at chapter 8.